Okay, I'm going to make this about myself again. Our speaker's from U of T as well. And it's not University of Texas, it's the appropriate T. You got to figure that out for yourself. Okay, Mina, just go ahead.
Hello. Yeah. Maybe the slides needs to. Is it not picking up with the slides? So hello everyone, my name is Mina Al-Masri. I'm a kernel networking engineer at Google, and I'm giving this talk on behalf of Willem de Bruijn, Eric Dumazet, and Kai-Wan Zhang, who are also kernel networking engineers at Google. And this talk is about device memory TCP, which is a proposal from us to transfer data to and from device memory efficiently. So starting with a little bit of a description of the problem space, the context here is large ML jobs, or specifically ML jobs that run across multiple nodes. Typically, these ML jobs would have data in the GPU, and they need to communicate across each other using GPU to GPU transfers in order to do whatever the useful computation that they're doing is. And in this specific context, the GPU to GPU transfer performance is critical to the performance of this job. So just for information, I have an example of a couple of typical communications in this context. The one on the left is all gather, where all nodes gather data from the other node's GPUs to its local GPU in order to perform some calculation. And the one on the right is a similar one called all reduce. And these are communication primitives that happen a lot across these multi-node ML jobs. If we zoom in on one of these nodes, I'll give a short overview over the software stack on one of these nodes. So typically you'll have an ML application running at the very top of the stack, and the ML application would call into some ML framework. You might have heard of them, PyTorch, TensorFlow are example. And the ML framework would delegate into a transport layer, or I'm calling it a transport layer. I think it's more commonly known as like a communications layer, which handles the cross-node communication. And the transport layer could have multiple implementations, TCP-based implementations, TCP transports exist. Also an alternative to that is RDMA transports. And in the case of TCP transports, it'll talk to a TCP stack in the kernel, of course, and the TCP stack will handle the connection. Now, one big issue with the TCP-based transports is that they require a host balance buffer. So the TCP stack typically doesn't interact directly with any kind of GPU memory. So any data that you really want to send or receive across the TCP, it needs to first be copied into a host memory balance buffer. And there are a couple of big issues with that. The first one is it consumes memory bandwidth. And the second one is that it consumes PCIe bandwidth. Consuming memory bandwidth is kind of straightforward. You need a lot of, you need some memory bandwidth to handle this GPU to host memory copies. And depending on how you've configured your hardware, it might be a genuine bottleneck, or at the very least, if you're trying to do something else that's useful with your memory, you might run into issues with hitting the bandwidth. The PCIe bandwidth utilization issue is a little bit more nuanced. So if you're doing device memory, if you're doing these GPU to GPU communications over regular TCP, you can imagine for each incoming packet, it comes in on the NIC. It needs to be sent all the way to a root complex across the PCIe hierarchy to get to the host memory buffer, and then it needs to be sent back down across the PCIe hierarchy to go to the GPU buffers where it's actually useful to the ML framework and the ML application running on your node. That really stresses shared PCIe links. Like in this particular diagram, you can see a PCIe link between the switch and the CPU, or the switch and the root complex, and each RX packet is really going over that link twice. And again, depending on your hardware configuration, for example, for Google Cloud A3 VMs, we have 8 H100 GPUs, same as in GGX systems. And if you have a lot of these NIC and GPU pairs sharing PCIe links, it can be a genuine bottleneck. So the proposal here is, well, unsurprisingly, device memory TCP. Device memory TCP, in its core, it's quite simple. Instead of sending the data all the way to the root complex from the NIC and then back to the GPU, this red arrow is modified. So we send data directly to the GPU in this case of RX, and we transfer data directly from the GPU in the case of TX. There are two arrows here because the packet payloads go straight into device memory, but the packet headers can still go into host memory for regular host memory processing. Yeah, there's an RFC on the mailing list. It's linked here. If you have access to the slides, you can take a look at the RFC as well. So that was a very short sort of overview of the proposal. Most of the rest of the slides will actually go into the nuts and bolts on how to implement this. So the very first step, yeah, and we'll go over this maybe a little bit chronologically. So from the device memory setup to the NIC setup to the connection setup, and then finally what happens on an RX packet to accomplish this straight to device memory. And we'll start with the RX path, which is much more interesting than the TX path. So the very first thing we need to do is pick a abstraction for the device memory. The abstraction of choice here is DMA buffs. If you haven't used DMA buffs before, they're sort of like the standard in-kernel abstraction for device memory, or I think the most common one. Typically the driver that owns the device memory will be a DMA buff exporter. It'll implement sort of like the APIs that the DMA buff interface requires. And whatever is using the device memory will be an importer. So in this case, the networking stack is sort of the importer of this device memory. A critical thing to note about DMA buffs is that they're not struct pages. DMA buffs typically, they refer to a region of memory, not struct paged. You really just get DMA addresses, like a list of DMA addresses for this region of memory. And really the use case is just like DMAing from and to this DMA buffer. And this is an important sort of thing to call out. It's gonna be very important later on because the networking stack is, of course, all struct pages, I think. Yeah. So the very first step in one of these to use device memory is that the user application will allocate device memory or GPU memory and then obtain a DMA buff handle to this device memory, and all of that is using standard APIs that already exist. The next step would be the NIC setup. So now we're getting into stuff that we added as part of the proposal, where the user binds an RxQ from the NIC to the DMA buff. And we'll talk about that, what that means, but really conceptually it means that the page pool that is serving this RxQ will now allocate memory from the DMA buff instead of going to the buddy allocator and allocating regular host memory pages. Other things that need to happen in order to set up the NIC is that we actually need to make sure that the data that we care about is the one that is steered into the specific RxQ that we just bound our DMA buff to. So that's the next two steps. The first step is to configure RSS to steer away all flows that we don't care about away from our RxQs, so we don't get packets that we don't want on this RxQ. And the second step, the ethtool-N, is to configure flow steering, so that any the flows related to our ML application or whatever wants to use device memory, the Rx packets for those flows land on the specific queue that we just bound our DMA buff to. Yeah, so now we'll go into some details about how the page pool actuates that binding. The idea is really based on RFC from Jakub Kaczynski a few months ago now, I think. And it's sort of a simple idea of plugging in a memory provider to the page pool. A memory provider these are the ops for the memory provider. It's quite simple. It's just like an init and a destroy, an allocation function, a freeing function. And the idea is that when the driver needs a page for an incoming packet, it'll ask the page pool for a page. The page pool can, of course, recycle a page if it already has an available one, but if it doesn't, it'll normally go to the body allocator to allocate new memory. And instead, with this memory provider, you can plug in different memory providers that can provide different kinds of memory. So I think Jacob himself was looking into using it for like 1 gig backed memory regions, but in this case, we're using it for device memory. So the idea here is to create a DMA buff memory provider, which instead of just allocating pages from the body allocator, it allocates sort of page size slices from the DMA buff. And of course, the DMA buffs, like I said, they're not struct pages at all. So we created this new abstraction. Like the name is a work in progress. But we call them IOVs or page pool IOVs. And the page pool IOVs really contain just like a minimal amount of data to make this slice of memory that comes from a DMA buff useful. So a ref count, the page pool that it refers to, or that it belongs to, and sort of like what I'm calling like the chunk owner, which has sort of which enables me to get like the DMA address of the chunk, ref counts on it, and the virtual address, which is the address that we finally give to the user space to make this region of memory useful. Now we've created sort of like a new memory type, and we need to and there are a few components in the networking stack today that use struct pages and that sort of need to understand this new memory type. These components are specifically the page pool, the drivers, and skb frac t, which has a page pool inside of it. Which has a struct page pointer inside of it, and also like users of the skb frac t will also sometimes grab the page behind the frag. And when we initially looked at this, it's a lot of code sharing to go over all of these components and make sure that they all understand the new memory type, and maybe even impractical. So we actually utilized, I think, a trick that the kernel uses a lot, which is to set the least significant bit on a pointer and then cast it to another pointer. And then code that needs to understand that this can be that this is either a page pointer or an IOV really can check for the least significant bit, but code that doesn't care can use it or hold it as if it's a page pointer. And the code snippet on the right is really an example of this least significant bit. So you've got in the first function there, you've got the memory provider allocating an IOV and then setting the least significant bit and casting it to a page pointer and returning it. And then other code can check if it's really an IOV and do some special handling or get the page behind it if it's an IOV. So in this proposal, the page pool really does most of the heavy lifting. It's really like the only component that needs to understand that this is a different memory type. It handles basically any special casing that is needed for these IOVs. And this is an example here where if you're getting a DMA address of a page, you can the page pool can very easily check if it's really actually an IOV and do any special handling related to the IOV. Otherwise, it just treats it as a page and returns the DMA address that it's stored inside of it. Now going over to the other components that need to use struct pages. Of course, drivers use struct pages all the time and struct page pointers. But if they're using the page pool, actually the drivers today usually use the page pointer as an opaque token. They typically don't access the page pointer directly or do anything useful with the page pointer. If they want to do something useful with the page pointer, they give it back to the page pool and say, hey, get me the DMA address, for example, or something like that. And this is an example from the IDPF driver that was proposed or recently merged, where it's allocating a page from the page pool, and it could get the DMA address from the page, no problem. But I think it's sort of recommended to go back to the page pool and say, hey, actually you get me the DMA address in case there's something funny going on. And this works great for us because we can actually return IOVs to the driver from the allocation functions and then sort of require the driver to only use them as an opaque token and then give them back to the page pool if they want to do something useful with them. And then the page pool can handle any differences between IOVs and pages. So after this entire setup is done and the networking stack sort of understands a new memory type, it's time for RX packets to come in on the wire. The first thing the NIC needs to do is that it needs to split the packet into a header and a payload. This is required because the payload gets DMA'd into the IOV that really lives on device memory or GPU memory. For efficient data transfer, but the header is DMA'd into a header buffer that exists somewhere on the host. And the idea behind that is that the host can access the header in order to do TCP processing. And then the NIC will create a devmem SKB. A devmem SKB is an SKB where really all the frags actually exist on device memory and is inaccessible. The next thing that happens is that the SKB goes through the TCP stack. The TCP stack, I think, for the most part, doesn't need access to the payload, but there are a few cases in the TCP stack where it tries to access the payload either for a copy or for a checksum calculation or TCP dump, stuff like that. And we've added as part of the support in the TCP stack for unreadable frags or SKBs with unreadable frags. And with that, the TCP stack mostly works fine. And these are really the only cases where some quirks happen, where if you're trying to do like a software checksum calculation, it of course can't work because it needs access to the payload, which it can't. TCP dump, of course, can't show you the payload of the incoming packets. Again, it's in inaccessible memory. And zero copy loopback requires a copy, and you can't access device memory to execute that copy. So also loopback doesn't work. Now, once the SKB makes it through the TCP stack, it's finally time to give it to the user. We use socket APIs, and we added APIs to receive message in order to give the data to the user. And really, what we're doing here is that we're giving the user a pointer into the DMA buff and saying your packet landed in this specific location, DMA buff. So we do that via C messages. The kernel generates a C message that says your data exists on this offset into the DMA buff, and this is the length of the fragment that I just received. And then the user grabs the C message and they can access the memory in that offset of the DMA buff. Now with these fragments, we can't really recycle the pages behind them until the user tells us that they're done with them, because it's sort of like a form of zero copy RX. And we've added a setsock opt as a signal for the user to say, well, I'm done with this particular fragment of the incoming data, and you may recycle it or you may reclaim it if you want. So this is the devmem don't need setsock opt. That actually concludes the RX path. The TX path for device memory TCP is much simpler. The plan roughly is to create APIs to send message where you can pass the DMA buff into the send message API. And from there, really, it largely follows the zero copy TX code path in the kernel. The zero copy TX, of course, it doesn't copy, but it also mostly doesn't access the payload behind it. And really, the key here is to create an IOV iterator that is backed by these page pool IOVs instead of the struct pages, and go through the TCP stack as normal. And really, on the driver side, we need to just override the DMA address that usually comes from host memory with the DMA address that comes from device memory. So initial results, we have this implemented and working locally, working in production with Google A3 VMs. At the TCP level, we're able to hit pretty much line rate, or 96-97% line rate, with our NIC and GPU pairs. Our NICs on A3 VMs, they run at 200 gigabits per second, so that's 192 per NIC and GPU pairs, running with all our pairs really running in parallel. We have production workloads running on top of Nickel and PyTorch. We don't have other sort of like ML framework tested, but they should be fine as well since they reuse the transport layers. We get around 3x better throughput than regular TCP Nickel transports. There's an asterisk behind that because I don't think we've put a lot of effort into optimizing regular TCP transports, but these are the numbers that we see. And we do get comparable network efficiency compared to RDMA-based Nickel transports if the message size is large enough. Yeah, and possible future work, IO ring support is something that we're considering. I think Dave is giving a talk about this right afterwards. Also, dynamic queue management is something that we're considering or is in discussion on the mailing list, where instead of having the user sort of like bind the RX, bind the DMA buff to the RX queues, we can generate them on the fly, sort of tear them down on the fly if when the user doesn't want them anymore, and maybe even, I don't know, configure RSS and flow steering automatically for them. That's actually all I have, so thank you very much, and if you have any questions.
So I got one for you real quick. You say a message size. What message size are you needing to hit line rate? And do you have a graph of throughput based on message size?
It's around 1 megabyte or so, or slightly less than that to hit line rate. Although I'm not sure that's actually the minimum message size needed to hit line rate, but usually
Okay, but you haven't done a scan of like 4K messages up to 1 or 2 meg?
We have, but I don't have the data off the top of my head, but we have, yeah.
Yeah. Oh, sorry. So I might have missed this, but this is really cool work. I'm wondering when you would reach for this as opposed to like other solutions in the space. You know, like what do you see as the advantages of this versus something like, you know, RDMA, InfiniBand, et cetera?
Compared to RDMA, this works with regular TCP, so it's more flexible in terms of protocols, in terms of fabrics, and in terms of NIC support. Really, the features that we need from NICs are really header split, flow steering, and page pool support, and yeah, the flexibility is something that is valuable here. Yeah.
A question for the driver side. So I didn't quite understand. You have to closer. Yeah. Closer. Hello. Yeah. Okay. I didn't get. How do you signal to the driver to allocate pages from this other page pool, right? Because normally the driver allocates from the regular page pool.
Right. Yeah, I guess I did skip that part. The Netlake API implementation will sort of will leave something in the Netdev RxQ struct that says this RxQ, this is the DMA buff it should bind to, and then at time of creating the page pool, there's code to sort of check for that field, or at least this is the current implementation.
Okay, so
it needs the teardown of the RxQ.
Okay, but the driver doesn't have to care. It doesn't need two page pools, right?
No,
it's internal to
yeah.
The page pool, this new API.
It's internal to the page pool. The only requirement for the driver really is that it doesn't mess with the page pointers that it gets from the page pool. Right. I've looked at a couple of drivers. Drivers usually don't touch the page pointer at all, so it works great. The only exception seems to be page address, but you can't get the address of an IOV anyway. So yeah.
You're also doing a queue binding, so it's a page pool for queue binding.
Yeah.
You wanted to repeat that line.
Oh, yeah, there's a page pool to queue binding. We do a page pool to queue binding, yeah.
Hello, I have two questions. Yes. The first question is, does this require any hardware support? Because I'm not sure whether this requires P2P DMA or any hardware support.
It requires header split, flow steering. In the software, it requires page pool support, and that's it. It doesn't require P2P DMA support.
But he's right. The hardware, so you're giving it a buffer. You're giving the NIC a buffer from somewhere else. The NIC has to be able to write P2P.
Exactly.
So yeah, you can't allocate a buffer that you can't reach. That's the requirement.
Okay, thank you. The second question is, could this also work with SSD? Because there is a paper at the NSDI this year, which is called IOTCP, which is pretty much similar to this, except it's between the SSD and NIC.
Does this work with SSD?
Yes.
I think it works with any DMA buff, including UDMA buff, which I use for my testing a lot. So UDMA buff is backed by user memory. I've never tested with SSD, but I think it will be fine.
Yeah, that's cool. Thank you.
So I have a comment on the no driver changes required. There do need to be 2 page pools inside the driver for this to work. Either that or the driver has to be putting the headers in the descriptors.
Right. The headers, I guess they can go to a page pool that has the headers. Our GVE implementation has just like header buffers that it manages itself without delegating to a page pool. But yeah, it could be like 1 page pool for the headers and 1 page pool for the payload. And yeah, the headers are on the host memory. That's not done by the driver actually. So the whatever the function is that creates an SKB, it checks for IOVs and marks it for you, and also warns you if you're trying to mix them and stuff like that. So it's nice actually. The driver doesn't actually care. Yeah.
Oh,
You have another mic?
I assume that if the process using this crashes, that you don't need to set sock op, the buffers magically go back.
Correct. When the process crashes, the way the Netlink API is implemented is that it detects the crash and unbinds the queue. That's very important. But also the TCP connection closes, and all the references that we're holding, we basically free them all. Yeah. It should work. It's tested to work. Yeah.
There's a remote question. Sridhar is saying, is flow steering to a queue sufficient? And okay, can we pop up that question on the screen? Or will it be useful to associate a socket to a group of queues?
As long as the orchestration is done correctly, I guess, where the DMA buff is bound to all these queues and your flows are going to all these queues, it should be sufficient. Yeah.
Can you talk to the dynamic queue allocation? Is that you map a socket queue to something that magically pops up from the driver?
Well, like a few ideas are flowing around. So when you bind an RX, a DMA buff to an RX queue, you can also automatically recreate that RX queue and only that RX queue so that it refills its buffers and only that buffers. There could be also an alternative API where you're really just giving like a Netlink API to create a queue with this DMA buff and a queue pops up with this DMA buff, or create multiple queues with these DMA buffs. The whole idea, which I kind of glossed over, was that when you bind the DMA buff to an RX queue, you need the NIC to refill its posted buffers for the RX queue, and we do that via device reset today. But that's kind of sort of like an improvement over that.
So typically, when you read storage data that's coming from the NIC into the GPU, you need to massage it in some way. It's not just ready, available, but this seems to have the DMA transferred directly from the network into the GPU, which would require that the data is just good to go for the GPU. Is that correct?
That is correct.
So is there any plan to do something where there is some sort of processing either on the NIC or the GPU to massage that data?
Maybe.
I think the answer is that's an orthogonal point, right? That's independent of this infrastructure. Whether once the data has landed, you can massage it as much as you want.
Exactly.
The point is, if you want to do a one hop through or a copy buffer, that's what exists today. This is making that hop unnecessary. And then you'll get it to wherever you need to process it, right? There is no...
But you still need to get the data ready for the GPU. Now you just have the GPU.
So there are two parts to this, right? I mean, this is also part to your previous question. You're thinking just ingest into the GPU network. The vast majority of the communication is GPU to GPU, which does not require any pre-processing. So, but the point is, if you want to land it in the CPU to process it, that's what you get today, right? There is no, you don't even just turn this feature off and you get what you want. right? This is to bypass the host memory. You're just going direct into the GPU. That's the whole point.
I think we'll wrap it up here. Thank you, everybody.